Okay, welcome back, class. Today's lesson is on center of mass. Center of mass, you can think of as like the balance point. So if you have something to kind of balance on your finger, you're going to place your finger right at the center of mass, and it will be perfectly balanced. For instance, maybe a ruler or something. And you know, for instance, let's say we had a just find a rectangle. I don't like that color. There we go. Okay. So you've got something, okay, and let's say you've got a big mass, whoops, a little mass there, and a big mass there. So maybe this is like 5 kilograms, and this is like 2 kilograms. Where do you think the center of mass would be? Well, it turns out you can calculate that. So let's just assume that this grid here equals 1. The interesting thing about center of mass is that you can make it as a calculation from any place you want that you call your zero. So for instance, let's make this line right here our zero line, okay? So figure we've got a center of mass I get used to this thing. Come on. Sometimes it works better than other times, I find. Maybe it'll get better with time. Okay, so we go for our line tool, and we go for black. Okay, so we've got a line from, say, here to here, representing the distance of our 2 kilograms, and we got a line from here, say, to here, representing the distance of our 5 kilograms. So let's call this distance 3 meters. This is 1, 2, 3, 4, 5, 6, 7, 8, 9.5 meters. So it turns out the way we calculate our center of mass, we say the x-coordinate of the center of mass is just m1 x1 plus m2 x2 over m1 plus m2. So in this case, we have 2 times 3 plus 5 times 9.5 all over 7, right? So let me just calculate that out on my calculator. 2 times 3 plus 5 times 9.5 divided by 7 equals 7.6. 7.6 meters. So let's find out where that is. I'm going to make a little triangle for our center of mass. Let's see. 7.6, measuring from the same spot. 1, 2, 3, 4, 5, 6, 7.5, 7.6. Okay, let me just see if I can mess with that a little bit. 7.6, about there. So that's the balance point here. you can see that the balance point is much closer to the 5 kilograms than it is to the 2 kilograms. It's because the 5 kilograms are so heavy that we don't want to give it as much leverage as the 2 kilograms. You can see the basic formula for calculating this is pretty straightforward. The x-coordinate of the center of mass is just the sum of each mass times its distance. Okay? And if we were doing x and y, you would get the y-coordinate of the center of mass just the same way. So, for example, let me create a problem. Let's say that, let me just put my axes on for a second. All right, I'm going to go dotted, and I'll go in, say, red. All right, so I'm going to make some axes here. Let's see if I can put that right on top of the thing. Good. Okay. Now I'll make another axis over here. Something like that. All right, so let me call this one my x-axis and this one my y-axis. So imagine that a waiter or waitress is carrying a tray with 3 plates on it. Okay, so I'm going to put the 3 plates on. Let's see, I want a shape. I'll make the plates round. Okay, I'm going to put one at 3, 3. Okay, and I'm going to put one at 2, -2. And I'm going to put one at -3, 0. Okay, so let me label where these are. This is 3, 3. This is -3, 0. And this one here is 2, -2. So those are the x and y coordinates of the 3 plates that are on this tray. Let me see if I can make a tray. Okay. Here we go. How does this work? Something like that. Okay, so the question is, where should the waiter put his or her, waiter or waitress, put his or her hand? Let's assume the tray has no mass compared to the rest of this. Well, we have to know the masses of each of the plates. So let's give them masses. I'm going to make this one 3 kilograms. I'm going to make this one 2 kilograms. And I'll make this one 2 kilograms. So, what would we expect? Well, if you think about it, we're going to expect our center of mass to be closer to this one than to these two, because this one is heavier, right? So it's probably going to be somewhere equidistant from these two, but closer to that one. I wonder if it's going to be right up around here. Well, let's find out. What we know here is, let's see, if we were to do the x piece, okay, let's find the x coordinates of our center of mass, okay? So the x-coordinate of the center of mass is going to be equal to each mass times its x. So we've got 2 times negative 3 plus 3 times 3 plus 2 times 2 over 2 plus 3 plus 3, that's 7, right? So that's going to be, let's see, 2 times negative 3 plus 3 times 3 plus 2 times 2. By the way, your graphing calculator knows order of operations, so I didn't have to use any parentheses there because it's going to do multiplication before addition. So I just typed in 2 times negative 3 plus 3 times 3 plus 2 times 2. Now I'm going to hit enter to get the answer. I'm going to divide by 7, and it turns out that the x-coordinate is 1 meter, assuming this is all meters. Let's try and see what we get for the y-coordinate. Okay, so the y-coordinate, the y-center of mass, is going to be 2 times, now that first one has a y of 0, plus 3 times, that one has a y of 3, plus 2, and that one has a y of negative 2. Once again, all over 7. And that gives us, well, basically we've got, I could do this in my head almost, 9 times negative 4, negative 36, divided by 7 is interesting. How would that be? Is that right? 0, 3, negative 2. Okay, so that is at negative 5. Oh, wait a minute. 9 minus 4. Let's try that again. Oh, I did 9 times, that's why. 9 minus 4, that's 5, divided by 7 is 0.7. Okay, that's better. 0.7 meters. So let's see if we can find out where we should put our center. All right, it should be 1 to the right and 0.7 up, right about there. Oops. Okay, so that's interesting. Okay. I guess it's not as close to that as I imagined, because these two, you have to remember, are balancing out that 1. Anyway, that's the balance point. It's pretty interesting that you can figure that out. I could give you one to try. Let's just make one up so you can go through the motions yourself. Okay? Let's see, what kind of situation could we have here? Let's say we've got, well, interesting. I'm going to do, imagine you have 2 weights, okay? We got one here, a big one, and a little one. And they're on a string. The string doesn't weigh much. But it attaches these 2 weights together. You throw these up in the air, an interesting thing happens that I will explain to you in just a minute. Well, not in just a minute, but after we do this problem. But for right now, for reasons that you may or may not guess, I want us to find the center of mass of this system. And let's just assume that the string doesn't weigh anything, okay? And that the distance between these two, center of mass to center of mass, is 5 meters. And let's make this a 2 kilogram mass, and let's make this a 7 kilogram mass. And we want to know, where is the center of mass? So first thing I'm going to suggest to you is that we have the habit of thinking X going across sideways and Y going the other way. But the truth is that you can do it any way you want, right? And so I'd rather make my x-axis go this way because it's a natural measurement. As a matter of fact, when we do our calculations, look at this. You could have, if you made the x origin right here, calculating your center of mass would be so easy because the distance for this one is 0. You only have to deal with the distance for one of them. Very interesting. So why don't you go ahead and see if you can calculate where the center of mass is for this. Okay, I'm going to go ahead and let you pause the recording and work on this problem. Okay, let's see if I get the same answer you got. One thing I want to try, I don't know if I can pull this off, but let's see, if I select all this stuff, I can rotate it all. I guess that didn't work. It was an idea anyway. What if I select it all? Can I group it? Because I kind of would like to rotate it, but I don't think that I have that ability. Okay, so we're just going to have to rotate it in our imagination, okay? So we're going to make the x-axis, okay? Let me just make an x-axis. Pay no attention to Excel starting up. Okay, so we're going to start our x-axis right here and run it out that way. Okay, that's our x-axis. So remember that the x of the center of mass is just x1, m1 plus x2, m2 over m1 plus m2. So in our case, the x of the center of mass is 0 times 7 plus 5 times 2 over 9. That goes away. 10 divided by 9 . 1.1. So our center of mass is actually right around here somewhere, interestingly. It's barely outside. That's the balance point right there between those two. And this has to do with things like binary stars and stuff like that. They rotate around their center of mass. So when you see something where you'll see what looks like a body in the heavens that looks like it has a wobble to it, like it's rotating around some point that's not at center, then you figure there's probably a satellite out there somewhere, and they're both rotating around some center here, and that this center is causing it to look like this one is wobbling, and you can't see this one because it's too small. This is used a lot by astronomers to detect moons and things like that. The interesting thing is that if you have a system like this with no external forces, we've got this thing that we call the velocity of the center of mass, okay? So basically this point, no matter how much these two move relative to each other, the center of mass is going to continue along with the same velocity it had, just according to Newton's second law. There's no external forces on the system. You can pretend that all the mass is concentrated on this one point, and it will follow Newton's laws, just like it was a 9-kilogram mass right here. And if there's an external force on it, it will accelerate like a 9-kilogram mass. And this is the piece that will accelerate. As these parts move apart and together, that center of mass, for instance, if it doesn't move in the beginning, it won't move in the end. If it has a velocity in the beginning, it has a velocity in the end. And you might ask, how do we know that? Well, it's very interesting because, well, maybe you can sort of have a little trust that we would define the velocity of the center of mass as m1 v1 plus m2 v2 plus whatever m3 v3 over m1 plus m2 plus m3. What we're doing here, this is like a weighted average. You see, we're weighting with mass the three velocities. So if something has a higher mass, its velocity is weighted more. And then we divide by the sum of all the weights so that we sort of, it's like the way they weight grades, you know. They would maybe multiply your test score times 7 and your quiz score times 3, and then they divide the whole thing by 10 to figure out your weighted score. The interesting piece here is that look at this top thing. Does it remind you of anything? Have you ever seen that before? Hopefully you will realize that that is the momentum, or the sum of the momentums right there. We know that's conserved. Well, if that's conserved, dividing that by the weight, masses, is going to be conserved also. So this velocity of center of mass never changes. So that's pretty much all we're covering here about center of mass. So sometimes you'll have problems, and you can, just like we could say the momentum before is the momentum afterwards, you can also say the velocity of center of mass before is the velocity of center of mass afterwards. And you can use that to solve problems as well. It's really the same thing. It's just a scale factor between the two. I wonder if I think we're good. So I'm going to call this the end of our center of mass lesson, and you can go ahead and try the problems in the book. All right, I'll see you soon. Bye. See if I can get back to my thing here.